Have we finally found the answer to one of humanity's oldest questions? Are we alone in the universe? The James Webb Space Telescope may have just brought us one step closer to a revolutionary discovery. Meet K2-18B, a distant exoplanet that has suddenly found itself at the forefront of astrobiological research. Why? Because James Webb discovered something unusual in its atmosphere, something that could potentially signal the existence of life. Water vapor, methane, and even the rare dimethyl sulfide are not just random molecules. They may be the biosignatures we are looking for, clues that life in some form exists beyond Earth. Armed with the most advanced space technology ever created, James Webb is our new guardian of the galaxy, a telescope designed to peer into the unknown and perhaps redefine our understanding of life itself. So, are you ready to venture into the unknown and dive into the mysterious world of K2-18B? As we venture deeper into space in search of answers to questions that have puzzled humanity for generations, we rely on the eyes of our technological marvels to bring the universe into focus. One such eye is the James Webb Telescope, or JWST. For decades, the Hubble Space Telescope has been our window to the universe, producing images that have both delighted and enlightened us. But even Hubble has its limitations. Meet James Webb, a telescope dedicated to pushing the boundaries of what we can see and understand. One of the most innovative features of the JWST is its cool screen technology. This is no ordinary sunshade. It's a multi-layered engineering genius the size of a tennis court that blocks the heat of the sun, earth, and moon. Why is this important? Because it allows the telescope to cool to incredibly low temperatures, increasing its sensitivity to the faint infrared signals emitted by distant celestial bodies. Infrared observations are crucial for studying exoplanets such as K2-18B. Unlike visible light, which can be absorbed or scattered by space dust, infrared waves can overcome such obstacles, giving us clearer and more detailed images. JWST's ability to make infrared observations is not just an achievement, it is a revolution in the way we study distant worlds. So what discoveries await us when we turn his gaze to K2-18B? Located 124 light-years away in the constellation Leo, this exoplanet is more than just a distant rock. You may have heard of the Goldilocks zone, a term describing the habitable zone around a star where conditions are ideal, neither too hot nor too cold, for liquid water to exist. K2-18b orbits around its parent star, K2-18, in just this zone. But what sets it apart from other exoplanets in similar orbits? K2-18b is not just another rocky planet. It is what scientists call a Hycean world. Hycean worlds characterized by a hydrogen-rich atmosphere and a surface covered by a watery ocean represent a new frontier in our search for extraterrestrial life. They offer conditions that may be similar to those around hydrothermal vents on Earth, which are known to support diverse ecosystems. Recent observations by the James Webb Space Telescope have revealed intriguing details about the atmosphere of K2-18b, from water vapor to methane and even potential traces of dimethyl sulfide. The atmosphere of this distant world is a cocktail of elements and compounds that could support life, or at least life as we don't yet know it. The discovery of these atmospheric components has caused a wave of excitement in the scientific community. Researchers are full of excitement and speculation as they ponder the implications of these discoveries for astrobiology and the broader quest to understand the nature of life in the universe. Could this Hycean world with its unique atmospheric composition be the key to unlocking the mysteries of extraterrestrial life? And what might its unique conditions mean for the future of astrobiology? When we venture into the field of exoplanet exploration, one of the most challenging but rewarding aspects is the study of alien atmospheres. K2-18b, with its unique location in the habitable zone and intriguing atmospheric composition, provides a compelling example. While Earth's atmosphere is a mixture of nitrogen, oxygen, and gas impurities, K2-18b is a very different cocktail. This exoplanet's hydrogen-dominated atmosphere with traces of water vapor, methane, and perhaps even dimethyl sulfide is a treasure trove of scientific curiosities. Studying the atmosphere of an exoplanet more than 100 light-years away is not an easy task. It involves a technique called spectroscopy, which analyzes the light from the planet's parent star as it passes through the planet's atmosphere. Different molecules absorb light of specific wavelengths, creating a unique fingerprint that can be deciphered to determine the composition of the atmosphere. The infrared capabilities of the James Webb Space Telescope played an important role in these discoveries. The Mid-Infrared Instrument Spectrograph, abbreviated MIRI, allows for an extended range of wavelengths, allowing it to detect a variety of molecules that were previously elusive. The presence of methane and the lack of ammonia in K2-18B's atmosphere has scientists speculating about the types of life that might exist there. On Earth, methane is often produced by biological processes, and its presence on K2-18B opens up the possibility of life forms that thrive in a hydrogen-rich environment, something we've never encountered before. The composition of K2-18B's atmosphere also suggests the presence of a subsurface ocean. This opens up exciting questions about atmosphere-ocean interactions and how these dynamics might affect the overall habitability of the planet. So could its atmosphere be the key to a new understanding of habitability and life beyond Earth? When we think of life, we often imagine Earth-like environments, but in fact life exists in environments where we can't even imagine. Studying extremophiles, organisms that thrive in extreme environments, opens up new possibilities for studying life beyond Earth. Deep in Earth's oceans, hydrothermal vents spew hot, mineral-rich water, creating an environment devoid of sunlight, but teeming with life. Extremophiles such as the thermophiles and acidophiles thrive there, challenging our traditional understanding of what life needs to survive. Could such life forms exist on exoplanets like K2-18B? The hydrogen-rich atmosphere of K2-18B offers unique conditions for previously unexplored life. On Earth, certain microbes called methanogens produce methane in an oxygen-free environment. If methane in the K2-18B atmosphere is produced biologically, we may be in a world where hydrogen-loving extremophiles thrive. The study of extremophiles expands the range of conditions in which life can exist. From the acidic rivers of Rio Tinto in Spain to the tundra of Siberia, life on Earth exists in a wide variety of extreme environments. This diversity encourages us to reconsider the ecological limits of extraterrestrial life. The potential for a subterranean ocean and hydrogen-rich atmosphere makes K2-18B an attractive target for studying extremophiles in the exoplanet environment. Perhaps this distant world has its version of extreme life, adapted to the discovery of DMS on K2-18B. While some consider it a strong candidate for biosignatures, others warn that abiotic processes can also produce similar compounds. The debate emphasizes the complexities and challenges in interpreting exoplanet data. Historically, astronomical discoveries have often been met with skepticism. When Galileo first discovered the satellites of Jupiter, His findings were initially rejected by many. Similarly, the discovery of the first exoplanet in 1995 was met with caution. These historical examples serve as a reminder that skepticism is an integral part of the scientific process. The search for extraterrestrial life doesn't depend on a single molecule or observation. Scientists are looking for a combination of biosignatures to create compelling evidence for the existence of life. Could DMS be a part of a larger puzzle involving other biosignatures like methane and water vapor? The debate's likely to continue until additional data is collected. As technology advances, future missions with even more sensitive instruments may provide the confirmation needed to classify the DMS as a true biosignature. Is DMS the key we have been waiting for in the search for alien life, or is it a distraction that is throwing us off track? Either way, the debate itself is a testament to the ever-evolving nature of scientific research. The James Webb Space Telescope has revolutionized our understanding of exoplanets like K2-18B, but it's just one step in a long journey of space exploration. What lies beyond this monumental mission, and how will future technologies continue to expand our cosmic horizons? The extremely large telescope, scheduled for completion by 2025, promises to be another game changer. With a main mirror diameter of 128 feet, it will be the largest near-infrared optical telescope in the world. Its unprecedented sensitivity could confirm or refute the biosignatures detected by the James Webb Space Telescope. The Large UV Optical IR Surveyor, or LUVOIR, is another mission on the horizon that could complement James Webb's findings. Designed to operate over a wide range of wavelengths, LUVOIR can provide even more detailed atmospheric analysis and potentially obtain direct images of exoplanets. As we target more distant exoplanets, advances in propulsion technology will be critical. Components like ion propulsion and even theoretical methods involving antimatter propulsion could drastically reduce travel times, allowing probes to reach and study exoplanets within a human lifetime. We've previously published a video on the possibility of interstellar travel and the challenges associated with it. As we stand on the threshold of potentially revolutionary discoveries, it's worth pausing to consider the philosophical implications and questions that fuel our cosmic curiosity. What does the search for extraterrestrial life mean for our understanding of existence, and what questions does it pose for the future? One question that's becoming relevant is the role of red dwarfs in the galaxy. Could these numerous stars, often overlooked because of their small size and dim light, actually be the cradle of life? Their longevity and stability make them intriguing candidates for planets that have life. What will the discovery of extraterrestrial phytoplankton mean for our understanding of life? Such a discovery would not only confirm the existence of life beyond Earth, but would also suggest that the building blocks of life are more universal than we thought. What will the next decade reveal in our quest to understand the cosmos? Will we confirm the existence of extraterrestrial life? Or will we discover new, even more complex questions that challenge our understanding of the universe?